Hello, welcome you all in the fifth part of the ultraviolet and visible spectroscopy. In the fourth part, we have discussed the Woodward-Fieser rule for the calculation of lambda max of Dine system. In this part, we will discuss the Woodward-Fieser rule for alpha beta unsaturated carbonyl compound, which are called as the enones, alpha beta unsaturated acids, and alpha beta unsaturated esters. By using these rules, we are going to calculate the lambda max values for enone system basically. So let's begin with the Woodward-Fieser rule for enone as well as acid and ester. All this table represent the Woodward-Fieser rules for the calculation of enone system, alpha beta unsaturated acid and alpha beta unsaturated esters. In the first table, there is a parent skeleton and they are having a specific base value. For acyclic and hexacyclic enone, 215 nanometer. For pentacyclic enone, 202 nanometer. For alpha beta unsaturated aldehyde, 207 nanometer. Whereas for alpha beta unsaturated acid and ester, 197 nanometer is the base value. Then, in addition to this, in case of substituent, we have to consider their position in the compound. So let us consider this structure. In this structure, this is the functional group, that is carbon double bond oxygen. With respect to this functional group, this is the alpha carbon. This is first carbon near to the carbonyl group. Then this is the beta carbon. This is the gamma and delta and so on. So the substituent which is present on this alpha carbon, it is called as alpha substituent. It is the beta, it is the gamma and delta. Now, when alkyl group is present or ring residue is present at alpha position, we have to add 10 nanometer. For beta position, 12 nanometer. For gamma, delta and above delta, we have to add 18 nanometer in the base value. Similarly, for alkoxy group, for alpha position 35 nanometer, for beta 30, gamma 17 and for delta 31. For hydroxy 35, 30 and 50 depending upon the position. For thioether, for beta position we have to add 80 nanometer. For chloro 15 and 12 nanometer should be added in the base value. Then for bromo 25 and 30. For acyloxy, we have to add 6 nanometer when this acyloxy group is present at alpha, beta or delta position. For amino group, we have to add a 95 nanometer when it is present at a beta position. Along with this, we have to consider the nature of double bond while calculating the lambda max value. For extended conjugation, 30 nanometer. For homodiene compound, 39. When exocyclic double bond is present to one ring, that is 5 nanometer. For two ring, or 10 nanometer. To understand these concepts, let us consider the second structure. Here you can see the enone system. It is from this CO group to this carbon double bond carbon. Now, this is the carbon double bond carbon which is in conjugation with this carbon double bond carbon. So there is a extra conjugation which is called as a extended conjugation. The value for this enone system is 215 nanometer. Then in the 215 nanometer we have to add 30 nanometer because there is a extended conjugation. Now, homodiene compound, it means that when two double bonds are present in a same ring and these two double bonds are conjugated, then there is a homodiene component. So in the ring B, the two double bonds are present and they are conjugated. So this is the homodiene component in ring B. Therefore, we have to add 39 nanometer. Exocyclic double bond. this double bond which is present outside the ring A and it is attached to the ring A through one carbon. So it is the exocyclic double bond. So we have to add 5 nanometer, and then after the addition of this component we get final lambda max value. Then furthermore we have to consider the solvent shift, in which solvent the UV spectrum is carried out. So when chloroform, dioxane, diethyl ether or hexane and cyclohexane is used, we have to subtract these values as from the lambda max values. But in case of water, we have to add 8 nanometer in the lambda max value and we get final wavelength of that organic compound. So by using this rule, we will see the different examples and how the lambda max value is calculated for that examples. In the calculation of lambda max for enone system, we have to identify the enone system. So to identify the enone system, just we have to look upon the structure of the organic compound, and there should be the presence of carbon double bond carbon which is in conjugation with the carbon double bond oxygen. Now in case of first compound, the enone system, it is extended from this carbon double bond carbon to this carbon double bond oxygen. Now second stage or second step is that we have to label the alpha, beta, gamma, delta substituent. So here this is the alpha substituent and this is the beta substituent. No gamma, no delta substituent. This is the methyl group which is attached to the carbon double bond oxygen. This is not the substituent. Now the base value for acyclic enone is 215 nanometer. Then for alpha substituent, here I will write alpha substituent, the addition is 10. For beta substituent, addition is 12. No solvent is given here, so no subtraction or no addition for the solvent. Then we have to add these terms, and here finally we get here the value that is 237 nanometer. It is the wavelength, that is lambda max value for this compound. Then the second compound, here you can see there is a cyclic compound and it is the 6-membered one. So it is the hexacyclic, and for hexacyclic just label or mark this enone system. Then value is 215 nanometer. Then second step, the labeling of alpha and beta substituent. This is the alpha substituent, and after this carbon this is the beta substituent. Now it is the part of cyclic ring, therefore it is the ring residue. So here I will write alpha substituent, it is the alkyl group. So here I will write 10 nanometer. Beta substituent, and beta substituent is a ring residue, so value is 12. Now again cyclic ring is there but no exocyclic double bond, no extra conjugation, no homodiene component, so final answer will be 237 nanometer. The third compound, it is having two ring, that is first A and B. Now here I will mark this enone system, it is the enone system. So it is the hexacyclic, therefore the value is a 215 nanometer. Now second stage or second step, it is the marking of alpha and beta and gamma and delta. This substituent, it is the alpha substituent. Here no beta, no gamma, but there is a presence of delta substituent. So here we can write 1 alpha substituent, and it is the ring residue, so value is 10. Then a delta substituent, For delta substituent, value is 18. Now, this double bond, it is in conjugation with this double bond, so this is the extended conjugation. So I have to write here one extended conjugation. So for extended conjugation, we have to add 30 nanometer. Now, in the ring B, these two double bonds, they are in a conjugation and present in a same ring. So this ring possesses a homodiene component. So here there is a addition of homodiene component, and for that purpose we have to add 39. Now the exocyclic double bond. Look here, this bond, it is marked by this blue color. This is the exocyclic double bond to the ring A. So one exocyclic double bond. So for one bond, we have to add 5 nanometer. Then by addition of this, all the values, we get here a lambda max value, that is 317 nanometer. In this example, this is the enone system. So carbon double bond oxygen and carbon double bond carbon, and it is having a 5-membered ring, so it is the pentacyclic. And for pentacyclic enone system, the base value is 202 nanometer. Then alpha substituent is present here. This is the alpha substituent, this is the beta, then no gamma, but there is a presence of delta substituent. So alpha substituent, it is the ring residue. So for that purpose, a 10 nanometer. For beta substituent, here a 12 nanometer, and for a delta substituent, we have to add a 18 nanometer in the base value. So again, afterwards, this is the single bond and this is the double bond. Therefore, this double bond is in conjugation with this bond. So there is a extended conjugation. Extended conjugation. So for that purpose, a 30 nanometer should be added. And here, this bond, I will mark with the green color. This bond, it is exocyclic to this ring. So there is a presence of one exocyclic double bond, and therefore we have to add a 5 nanometer. So by adding this all the values, we get the final answer, that is 277 nanometer. Now, the next example, it is having a 6-membered cyclic ring and the base value is 215 nanometer. Now, this is the enone system, and here alpha substituent is absent but beta substituent is present. So here I will write a beta substituent, and the beta substituent is a chlorine, and for chlorine we have to add a 12 nanometer. Now this is the beta chloro. Then this bond, it indicates the ring residue. So here again a beta substituent, which is nothing but the ring residue. So I will write here a ring residue. For that purpose, we have to add 12 nanometer. Now here there is a presence of ester group, but this ester group is not a part of the enone system. So we will neglect this ester group. Now, along with this, there is no presence of extra double bond or exocyclic double bond. So just we have to add these values, and after adding these values, we get the lambda max value for this compound is 239 nanometer. Now, the final compound, it is having 3 rings, that is ring A, B, and C. Now, the enone system, it is like this. After enone system, there is a single bond, double bond, single bond, double bond. So two extra conjugations. First of all, I will write the basic value. Then I will put here alpha, beta, gamma label. So this is the beta substituent. Then here alpha absent, beta present, gamma absent, delta absent. And above delta, this is the first, and this is the second, and this is the third. So above delta, we have three substituents. So first of all, I will write a beta substituent, which is nothing but the ring residue. And for that purpose, we have to add 12 nanometer. Then delta, that is above delta substituent. For that purpose, we have to add 18 nanometer for one substituent. So there are three substituent. So total of 54 addition. Now extra conjugation is there. This is the first extra conjugation. This is the second. So two conjugations. So for one conjugation, we have to add 30. For two, it is 30 into 2, that is equal to 60. Then exocyclic double bond. Now for ring A, no exocyclic double bond is present. For ring B, this is the ring B. For that, this bond and this bond, these two bonds are exocyclic. So two exocyclic double bond for ring B. For ring B. So total value 5 into 2, it is equal to 10. By adding all these values, we get the lambda max value, that is 351 nanometer. In this way, we can calculate the lambda max values for various organic compound by using Woodward-Fieser rule.